Welcome back to Climate Dynamics. We're finishing off our discussion now on convection by focusing on moist convection. The reading again is Marshall and Plum, Chapter 4. In this section, we're going to discuss various quantities related to measuring moisture in the atmosphere, including specific humidity, saturation-specific humidity, relative humidity, dew point temperature, and lifting condensation level. We'll also be talking about moist static energy, conditional stability, and equivalent potential temperature. The key questions that we aim to answer in this section are: how does moisture affect convection? What differentiates dry and moist convection? And why is convection a prominent feature of the tropics? Finally, we assess what are the global hotspots for convection. You will observe throughout this lecture that much of the framing that we did in the case of dry convection continues to hold. That is, these notions of stability and instability are still relevant even in the case of moist convection. We simply add an additional layer of complexity associated with moisture. Alright, before we begin, we need to go over some basic definitions related to moisture in the atmosphere. The first definition is that of specific humidity, which is typically denoted with a lowercase q. This is simply the mass of water vapor per mass of air. That is, the numerator is the total mass of water vapor, and the denominator is the total mass of air, including both dry air constituents and water vapor constituents. This can also be written in terms of density, because volume divides out from either side. Consequently, we can write Q as the density of water vapor divided by the total density of the air. If an air parcel experiences no condensation or evaporation, then the specific humidity is conserved following the fluid parcel in accordance with the law of conservation of mass. The second definition we need is saturation-specific humidity, which is closely related to the saturation vapor pressure that we discussed earlier in the context of the Clausius-Clapeyron relationship. Here, saturation-specific humidity is simply a way of looking at that saturation vapor pressure in light of specific humidity. Specifically, the saturation-specific humidity is the specific humidity at which saturation occurs. Recalling that specific humidity is the mass of water vapor divided by the mass of total air, we can use the ideal gas law in order to write this as ES over RVT in the numerator and P over RT in the denominator. Although technically the R in the denominator here is associated with the R of combined vapor plus dry air, it is common to approximate this using the ideal gas constant for dry air. The reason being that the contribution because of water vapor is relatively small. Once this is done, we obtain Q star equal R over RV times ES over P. Here again, ES is the saturated partial pressure of water vapor obtained from the Clausius-Clapeyron relationship, which is again a function of the local temperature of the air. Alright, so what's the behavior of this saturation-specific humidity with altitude? Given that we know that specific humidity is conserved following a fluid parcel, then it follows that a rising fluid parcel will need to pay most attention to the behavior of the saturation-specific humidity in order to determine the height at which condensation will begin to occur. We can assume a constant lapse rate environmental profile. Again, this is a pretty good approximation to behavior in the troposphere. Recall that it's very common in order to accept a lapse rate of about 6.5 Kelvin per kilometer in accordance with the International Standard Atmosphere. However, different environmental profiles are possible depending on where you are located and current meteorological conditions. What we can show is once we plug this temperature into the hydrostatic balance equation and utilize the ideal gas law, that the pressure profile induced by this particular linear temperature profile is given by the second equation shown on this slide. We can then use the saturation vapor pressure from the Clausius-Clapeyron relationship and plug that in addition to our vertical pressure profile, into Q star in order to obtain an expression for the value of Q star as a function of altitude. Alright, so the behavior is dependent on the surface temperature, here denoted T0, and the background lapse rate. We're going to assume for simplicity that the background lapse rate here is exactly 6.5 Kelvin per kilometer. Given that, we can then plot various curves associated with different surface temperatures. So, on the right-hand side here, we have a surface temperature of 310 Kelvin. The middle line shows a temperature of 300 Kelvin, and the leftmost line shows a curve associated with 290 Kelvin. Altitude goes up the y-axis, and the saturation-specific humidity, here given in kilograms per kilogram, is shown along the x-axis. What we see is that for larger values of the surface temperature, we can essentially retain more moisture within the air before condensation would occur, that is, before the parcel reaches saturation. This is consistent with our understanding of the Clausius-Clapeyron relationship. All the curves also seem to decay approximately exponentially with altitude. If one was to plot the specific humidity of a fluid parcel on top of this chart, essentially any fluid parcel that found itself to the right of the saturation-specific humidity curve would be considered supersaturated. Sitting on the saturation-specific humidity curve would produce a saturated parcel, and to the left would be unsaturated. Alright, let's define a few more quantities related to moisture in the atmosphere. Relative humidity is the ratio of specific humidity to the saturation-specific humidity, expressed as a percentage. Here, this is equal to Q divided by Q star times 100%. Relative humidity determines how close our fluid parcel is to saturation. That is, a fluid parcel with 100% relative humidity is exactly saturated. In nature, values of relative humidity larger than 100% are not commonly observed, because this implies that the parcel exists in a supersaturated state, and any small perturbation would immediately trigger condensation. The second definition we need is dew point temperature. This is the temperature at which an air parcel becomes saturated, or achieves 100% relative humidity when it is cooled at constant specific humidity. So, obviously, cooling the temperature of the fluid parcel will result in bringing the saturation-specific humidity down. This is because the saturation vapor pressure determined from the Clausius-Clapeyron relationship has a strong temperature dependence, with air being unable to hold as much water vapor at cooler temperatures. If the temperature drops below the dew point temperature because of cooling, then water vapor in the air will begin to condense. The third definition we need is the lifting condensation level. This is the altitude at which a rising air parcel reaches saturation, due to adiabatic cooling on ascent. Specifically, you can imagine that if you have a fluid parcel in the near surface that has some level of moisture in it, as it rises, it will cool, experiencing the dry adiabatic lapse rate. At some point, the saturation-specific humidity will have dropped sufficiently low that it matches the specific humidity of the fluid parcel. This is the point at which condensation will begin to occur if the air parcel continues to rise farther. Here are two environmental profiles. On the right-hand side, we have the environmental profile of the temperature, with a surface temperature of about 300 Kelvin, and on the left-hand side, we have the environment saturation-specific humidity in kilograms per kilogram for that same environmental profile. If we consider a parcel that begins at the near surface at 320 Kelvin and a specific humidity of 0.01 kilogram per kilogram, this parcel will then rise because it finds itself warmer than its surrounding environment. That rising motion will originally undergo a dry adiabatic lapse rate change in temperature. This is because no condensation is occurring within the fluid parcel. That is, our specific humidity is below the saturation-specific humidity, so there is no condensation that will be triggered because of an exceedance of 100% relative humidity. At some point, though, as you see in the left-hand plot, the specific humidity which is conserved following the fluid parcel will match the environment saturation-specific humidity, which is a function of the environmental temperature. When that occurs, we have reached the lifting condensation level of the parcel. Above this point, the fluid parcel will be undergoing the saturated adiabatic lapse rate because it is exactly at saturation as it rises. The saturated adiabatic lapse rate is less steep than the dry adiabatic lapse rate because condensation is occurring, which is simultaneously warming the fluid parcel. The exact saturated lapse rate is dependent on the environmental conditions. As the fluid parcel rises, condensation is occurring, and as we see in the left-hand plot, all of the excess water vapor beyond the saturation-specific humidity will be condensed out in order to form cloud droplets. Eventually, the rising fluid parcel will reach the level of neutral buoyancy. At this point, the temperature of the fluid parcel matches that of the background environment. The fluid parcel can rise no farther above this point. This is analogous to the process that occurred in the case of dry convection. That is, the fluid parcel continues to rise until it reaches its level of neutral buoyancy. Note that there is no cloud above this point. That is, at approximately 10 kilometers altitude, when the fluid parcel reaches the neutral buoyancy level, we have reached the cloud top. No additional condensation will occur above this altitude because the fluid parcel is not rising any farther. The fluid parcel at this point can of course expand laterally, but no further vertical motion will occur. Alright, let's examine the saturated adiabatic lapse rate quantitatively. In order to do so, we're going to go back to the second form of the thermodynamic equation and investigate how moisture enters into this equation. Recall that the second form of this equation consists of terms on the left-hand side that describe adiabatic motion. The term on the right-hand side explains diabatic heating, which includes concepts such as condensation. But exactly how much energy is released by condensation? Well, we'll have to go back to the fundamentals of moist physics in order to answer that question. Okay, note again that the CP here for dry air does not hold exactly, but because of the low moisture content in the air, it is still a good approximation. The latent heating from the moisture condensation again plugs into the right-hand side for the diabatic heating rate. The amount of energy released through condensation is encapsulated through a concept known as latent heating from condensation. In general, we know that the amount of heat released is going to be proportional to the change in water vapor within the fluid parcel. That is, the more water vapor that condenses, the more energy will be released. Thus, we can write the diabatic heating rate as being proportional to the change in specific humidity within the fluid parcel, which is the material derivative of Q. The constant of proportionality here is the latent heat of condensation for water. Note that here, and through the remainder of this lecture, and through our theoretical derivation, we will be approximating Cp and L as constant, although in reality they are dependent on environmental conditions. For a steady, horizontally homogeneous and hydrostatic fluid, that is one where the hydrostatic balance law holds, we can show via chain rule that 1 over density times dp dt can be written as the material derivative of negative gz. That is, it's proportional to the vertical velocity of the fluid parcel. Using this, we can then plug this left-hand side term into the second form of the thermodynamic equation in order to obtain a single quantity that is conserved following the fluid parcel, equal to Cpt plus Gz plus Lq. This quantity is known as the moist static energy of the fluid parcel. If moisture was not present, that is, if Q is equal to 0, then the first two terms of this expression would be known as the dry static energy. Note that this encapsulates different energy contributions to the total energy of the fluid parcel, including internal energy, potential energy, and any energy that comes because of the phase change of water. Okay, let's derive the saturated adiabatic lapse rate for a fluid parcel. To begin, we'll start by noting that the saturation-specific humidity is dependent on both the environmental pressure and temperature. So, by chain rule, we then have that the incremental change in the saturation-specific humidity can also be written in terms of the incremental changes in both pressure and temperature. Specifically, we have dq star equals dq star dp times dp plus dq star dt times dt. Now we can use the definition of Q star and plug that into this relationship. Specifically, we have Q star equals R over RV times ES, which is the saturation vapor pressure as a function of temperature, divided by P. Alright, the partial derivative of this with respect to pressure only impacts the pressure that appears in the denominator on the right-hand side here, because we know the saturation vapor pressure is purely a function of temperature. So, taking that derivative, we have dq star dp equals negative q star over p. The temperature derivative, on the other hand, needs to impact this saturation vapor pressure. So we can take a derivative of ES with respect to T and approximate that using a Taylor series expansion as a constant. The approximate scaling of this relationship with respect to temperature, then, is given by this beta quantity. Again, this is dependent on environmental conditions. But for this theoretical derivation, we can again approximate this as constant, and that constant comes out to be approximately 0.067 inverse degrees Celsius. With this approximation in hand, and plugging back the definition of Q star into this relationship, we then obtain di Q star di T equals beta times Q star. Hence, for a parcel at saturation, we have that the instantaneous change in saturation specific humidity is approximately given by negative Q star over P dP plus beta times Q star dt. For an air parcel that's continuously at saturation, the thermodynamic equation for that air parcel can be written in as the second equation shown here. And so, combining these two equations, specifically in order to eliminate the dq star term, we obtain the final expression shown below. This then relates the incremental change in temperature to the incremental change of pressure for a fluid parcel at saturation. Again, using the hydrostatic balance relationship, we have dP can be replaced with dz. Plugging that in and dividing through by dz then gives us an expression for the change of temperature with altitude. Specifically, recall that the lapse rate is defined by negative dt dz. From this equation above, we can calculate then dt dz and obtain this expression below. The resulting expression is quite complicated, and I don't expect you to memorize it, but it is a common expression for the saturated adiabatic lapse rate. What is important about this, though, is that the factor in the square brackets is always less than 1. So we know that the saturated adiabatic lapse rate is always less than the dry adiabatic lapse rate. Further, we can use this formula in order to estimate particular values of the saturated adiabatic lapse rate to get a feel for how it compares to the dry adiabatic lapse rate. Since Q star depends on temperature, there is not a single value associated with gamma S. However, the saturated adiabatic lapse rate is typically about 3 K per kilometer in the tropical troposphere. And it's very close to 10 K per kilometer, or approximately equal to the dry adiabatic lapse rate in the upper troposphere where Q star is negligible. Recall again that Q star decays approximately exponentially with altitude, so in the upper troposphere where temperatures are very cold, we anticipate that the ratio within the square brackets is very close to 1. On the right-hand side here, we see a schematic of the tropospheric temperature profiles showing dry and wet adiabats, and a typical sounding shown with the purple solid line in the middle. Alright, since the saturated adiabatic lapse rate is always less than the dry adiabatic lapse rate, that basically means that the moisture within the air parcel acts to destabilize it. That is, because the air parcel is warming as condensation occurs, a moist air parcel will be more unstable and can rise higher than a dry air parcel. That is, it has a greater chance of remaining warmer than the surrounding environment. Now, this is the stability of the parcel. If you have a moist environment, the opposite is true. That is, if the environment is moist and the air parcel is dry, then the moisture reduces the environmental lapse rate, leading to a more stable environment. Recall from our discussion of dry convection that the shallower the change of the background temperature with altitude, the more stable the surrounding environment. In both cases, the reduced lapse rate is because of condensation of water vapor, which occurs as temperature drops and leads to local heating. This is a form of negative feedback process. That is, as the air temperature gets cooler, you have more condensation, which acts to counteract the cooling effect from adiabatic rising. Alright, this incurs an important concept related to the stability and instability of these fluid parcels. Namely, we have this intermediate state where a fluid parcel will be unstable if it is moist and stable if it is dry. So, in this intermediate regime, we say that the environment is conditionally stable if it is stable with respect to dry air parcels, but unstable with respect to saturated air parcels. Namely, an environment with local lapse rate gamma is conditionally stable if its lapse rate gamma is greater than the saturated adiabatic lapse rate, but less than the dry adiabatic lapse rate. This is in comparison with absolutely stable and absolutely unstable conditions. In the absolutely stable case, the lapse rate is less than the saturated adiabatic lapse rate. So regardless of whether the parcel is moist or dry, it will nonetheless be stable. However, if the lapse rate is larger than both the dry adiabatic and the saturated adiabatic lapse rate, then the environment is absolutely unstable. That is, any fluid parcel will rise against this background profile. Alright, here's a depiction of what I described a moment ago. Namely, we have a saturated adiabatic lapse rate depicted with the dashed blue arrow here, and a dry adiabatic lapse rate depicted with the solid arrow. Recall the saturated adiabatic lapse rate decreases more slowly with temperature as one goes to higher altitude. The three red curves here depict various environmental conditions. Curve A on the far left is absolutely unstable. That is, its lapse rate is larger than the dry adiabatic lapse rate and larger than the saturated adiabatic lapse rate. Consequently, any parcel in this environment will find itself to be unstable and will rise against the background. Curve B represents conditionally stable conditions. That is, if the air parcel is dry, it will find itself stable. That is, a rising air parcel in this environment will find itself cooler than its surroundings, and so it will sink back down. However, if the fluid parcel is saturated, then as it rises, the warming from the condensation will enable the fluid parcel to remain at a temperature larger than that of the environmental conditions. Consequently, these are known as conditionally stable conditions. Finally, on the C curve, we have absolutely stable conditions. That is, regardless of whether the fluid parcel is dry or moist, it will find itself cooler than the surrounding environment, regardless of which curve it follows up in altitude. Consequently, it will always sink back down and will oscillate about its initial position. Okay, let's discuss another quantity that's related to the presence of moisture within the atmosphere. Recall in the dry convective context we discussed potential temperature, which is conserved following air parcels as they rise and descend. However, we acknowledged in that discussion of potential temperature that in the presence of diabatic forcing, such as condensation or evaporation, potential temperature is not conserved. Consequently, we are interested in deriving a quantity that is conserved, even approximately, in the presence of moist behaviors such as condensation and evaporation. Alright, let's start with the thermodynamic equation in the second form for fluid parcels with moisture. We're going to jump over some of the derivation that we performed for the dry potential temperature. On the right-hand side, though, we're going to recall that the diabatic heating rate is going to be proportional to the latent heat of condensation, denoted here with a capital L, and the change in specific humidity within the fluid parcel. There's also a CPT in the denominator that comes out of this derivation, and I leave it to you as an exercise in order to find out why. If we assume that temperature variations are small, then we can incorporate that temperature into the material derivative term on the right-hand side. Specifically, this pops out because Q is small as well. And so the product, Q times dt dt, will also be small. Consequently, this allows us to produce a single material derivative term incorporating L, Q, and CPT in the denominator. This is necessary because this term needs to be combined with the material derivative term that shows up on the left-hand side for dry potential temperature. So if this is combined and we simplify, we then obtain that the material derivative of this logarithm of potential temperature times E of LQ over CPT is equal to 0. That is, this quantity within the square brackets is conserved following fluid parcels, and this is also our theoretical equivalent potential temperature. Again, there is an approximation here that is associated with the small water vapor content within the atmosphere. I refer to you to a reference such as Holton's book on dynamic meteorology in order to understand more. However, for the time being, what we can acknowledge is that this equivalent potential temperature provides a better approximation for a conserved quantity in the presence of moist convection. Its expression is given here. And formally, the equivalent potential temperature can be defined as the temperature an air parcel would reach if all water in the parcel were to condense, releasing its latent heat, and the parcel brought adiabatically down to a standard reference pressure. That is, recall, for dry potential temperature, we were referring to fluid parcels that were brought down to a reference pressure of P0. In this case, we're adding also condensation of all of the moisture, all of the water vapor that is present within that fluid parcel as well. So one expects that the equivalent potential temperature then will be larger than the potential temperature, and the degree to which it is larger is proportional to the amount of water vapor within the fluid parcel. So, to summarize, equivalent potential temperature is conserved following an air parcel even if water vapor condenses during that pressure change. If air is dry, then Q equals 0 and the equivalent potential temperature reduces to the dry potential temperature. Note that vertical gradients of equivalent potential temperature tend to be mixed away by moist convection, analogous to gradients of potential temperature do in dry convection, or analogous to temperature gradients in a liquid. However, note that there were several approximations that we did make in the theoretical derivation a moment ago. And there are better ways in order to handle these issues if you needed a very exact measurement for equivalent potential temperature. One such derivation is described by Bolton in his seminal 1980s paper. Here, we can calculate the equivalent potential temperature in terms of the water vapor mixing ratio, the potential temperature at the lifting condensation level, as well as the temperature of the dew point at the lifting condensation level. I leave it to you in order to study this particular formula. Again, this is more useful if you need to have a very exact approximation for the equivalent potential temperature of a fluid parcel. The differences between the dry potential temperature and the equivalent potential temperature are largest in the tropics, where most fluid parcels are moist and often near saturation. In these regions, we can plot temperature, dry potential temperature, and equivalent potential temperature against each other as a function of altitude or pressure. What we see is that temperature tends to decrease as one goes to higher altitudes, as expected. The temperature change is not linear in this case because of changes in the water vapor content of fluid parcels. The dry potential temperature increases with altitude. As we've seen before in, for instance, our climatology of dry potential temperature, this is indicative of stability under dry atmospheric conditions. One would not anticipate ever seeing a decrease of theta with altitude unless convection was active in that particular region. Since convection is typically a small-scale feature, averages of potential temperature over large regions tend to always increase with altitude. If we plot equivalent potential temperature, though, what you do see is a slight decrease in equivalent potential temperature in the near surface and a roughly constant profile through much of the troposphere. This indicates that for saturated air parcels, the background environment is very close to being unstable. That is, presence of moisture within this environment can very easily trigger convection. This is consistent with our understanding of the tropical region, where there is significant convection induced by warm surface temperatures and significant moisture of individual fluid parcels. All right, on that topic, let's consider now isolating and identifying regions of the world where convection is active. All right. There's several different classifications of cloud types, and this class doesn't really delve into different cloud types, but what I'd like to emphasize is that when it comes to clouds that have any sort of vertical structure associated with them, we typically refer to either cumulus or cumulonimbus cloud types. Cumulus types are typically very puffy clouds, little fluff balls per se. These clouds are typically shallower than cumulonimbus clouds and have this puffy top associated with them. Cumulonimbus clouds are associated with deep convection and tend to produce heavy precipitation. These clouds can reach as high as the top of the troposphere and are responsible for producing things like anvil clouds. Typically, these cumulonimbus clouds can also be associated with thunderstorms, heavy rain, and sometimes even hail. The cumulonimbus clouds, again, have this characteristic anvil shape when they reach the tropopause. Again, that is because as air parcels rise through the troposphere, they will be bounded above by the tropopause, which is effectively a very stable environment. That is, it has constant temperature with altitude, hence potential temperature increases very rapidly in the background environment. This provides the opportunity for these air parcels to reach their neutral buoyancy point and hence will not rise any farther. The structure of the cumulonimbus clouds vary depending on the background temperature. For parts of the cumulonimbus cloud close to the ground, typically water exists in both vapor and liquid phase. Midway through the cloud, where temperatures are mixed, we have both ice and water, and then near the top of the cloud, we have pretty much only ice crystals because the temperatures here are so cold. Cumulus clouds, on the other hand, correspond to shallow convection and typically don't extend above approximately 4 kilometers above the surface. The lifting condensation level here in either case is approximately flat, and it is the point, the altitude, at which condensation begins to occur for a rising fluid parcel. Here is a depiction of the development of a deep convective storm. The towering cumulus stage is where the clouds take the form of these cumulus clouds. If there is sufficiently large updraft, or if the fluid parcel is sufficiently moist and the background sufficiently cold, we can have a fluid parcel that then rises quite high in the troposphere. Under strong unstable conditions in the background, these fluid parcels can again rise up to the height of the troposphere and produce condensation throughout the entire process, either in the form of liquid condensation or in the form of solid condensation, such as ice crystals. Precipitation is induced whenever these cloud droplets grow large enough in order to form rain droplets, or ice crystals. When they're sufficiently large, the winds are no longer able to keep these particles in the atmosphere, and so they'll naturally fall out in the form of precipitation. This is the mature stage in the development of these deep convective storms. Eventually, as moisture is removed from the system, we end up in the dissipating stage, where some remaining moisture continues to precipitate out, but otherwise the process leads to a moistening of the upper troposphere. Typical vertical velocities in cumulus clouds rarely exceed 2 meters per second. Temperature fluctuations are small, on the order of approximately 0.1 Kelvin, and the heat flux, because of vertical motions within the storm, is approximately 200 watts per meter squared. The deep cumulonimbus clouds are instead associated with dramatic heat fluxes, vertical velocities, and large temperature fluctuations against the background, with vertical velocities of up to 10 meters per second, heat fluxes of 10 kilowatts per meter squared, and temperature fluctuations on the order of about 1 kilometer against the background profile. Note that the heat fluxes that are produced because of the convective motion within these towers are comparable to radiative fluxes, so it is responsible for a dramatic amount of energy exchange between the surface and the upper atmosphere. Here are some images of cumulus clouds over Ukraine. Again, these are associated with shallow convection, but some vertical development. Here's an image of a cumulonimbus calvus cloud over the Gulf of Mexico in Galveston, Texas. Here we see the complete vertical structure of the cloud, as well as precipitation emerging from the bottom. Here are shots of cumulonimbus clouds from above, taken over Brazil. Here the source is from NASA. As we can see here, we have the typical anvil characteristics associated with these deep convective plumes. Further, we have multiple convective episodes occurring within the frame of this shot. The anvil-like structure leads to roughly flat anvil tops and spreading of the moisture content as it reaches the tropopause. Here's an example of a supercell, which is a giant cumulonimbus storm that is associated with a deep rotating updraft. These storms are notorious for producing tornadoes and hail over the Midwest and the Great Plains. In April 3, 2004, this particular supercell ended up dropping 2-inch diameter hail over Chaparral, New Mexico in the US. So where does deep convection occur? Well, we can actually use observations in order to understand better regions which are particularly susceptible to deep convection. Deep convection, which extends through the whole depth of the troposphere, is much more common in tropical regions, where equivalent potential temperature is approximately constant with altitude. In particular, the deep convection tends to occur in three primary areas. One, over Indonesia, or the western equatorial Pacific. Secondly, over Amazonia. And third, over equatorial Africa. In order to see deep convective episodes from space, we typically look at a quantity known as outgoing long wavelength radiation, which is a measure of basically terrestrial radiation emitted from the emission level. Where deep convective episodes are present, we typically have lower outgoing long-wave radiation values because the emission level is high in the atmosphere, which is associated with lower emission temperatures. Whereas higher outgoing long-wave radiation is indicative of higher emission temperatures, that is, emission that may be coming from the near surface. Here's a depiction of why this is the case. If we have a cumulonimbus cloud, then most of the radiative emission is coming from the cloud top, because emissions from the surface are effectively blocked by the cloud. Consequently, the emission temperature observed from space is going to be the temperature of the troposphere at the cloud top. Whereas under clear conditions, we have that the emission can come directly from the surface and hence will typically be much warmer, producing a warmer overall emission temperature. Looking at satellite records of outgoing long-wave radiation, we see that for the most part, these profiles match closely with what we've observed previously for the temperature variation over the Earth. That is, we see cold temperatures in the polar regions and warmer temperatures over the tropics and subtropics. This indicates that we have cooler emission occurring from the polar regions and warmer emission coming from the subtropics. Nonetheless, there are three very patchy areas across the equatorial band where we have very low outgoing long-wave radiation. These are the regions which are associated with very low emission temperatures, and are also the regions where we have strong convection. The strong convection within these regions then produces a lower outgoing long-wave radiation because of the emission coming from the cloud tops. All right, so where does convection occur? Recall, convection occurs where a warm surface is significantly warmer than the environmental air aloft. The most common mechanism in the tropics for this to occur is via warming of the surface via solar heating. In the mid-latitudes, on the other hand, there is another mechanism which commonly gives rise to convection. Recall, in these regions, we typically have cooler overall surface temperatures compared to the tropics and less moisture availability. Nonetheless, frontal activity can be responsible for the transport of cooler air aloft. Consequently, as cool air moves in, it can trigger unstable conditions, which can enable a fluid parcel to rise through the distance of the troposphere and produce deep convective episodes. So, for example, a passing cold front can trigger the onset of convection. All right, thank you very much. That's the remainder of the lecture for today on moist convection. Next time, we'll be talking about the general circulation of the Earth's atmosphere.